Hi class. In this lecture, what we want to do is we want to talk about probability for events involving the and statement. So it'll be something like, what's the probability that this and this occurs? And then I want to talk about conditional probability as well. Okay, so two objectives, find the probability of one event and a second event occurring. And then I want to compute conditional probabilities. Okay, so first off, when working with the and statement, you have to figure out if events are what we call independent events or dependent events. So we'll start with independent events. So two events are independent if the occurrence of either of them has no effect on the probability of the other. Like when you flip a coin two times in a row, those are independents because, whatever I flip first or whatever I flip second doesn't affect, the outcome of the other flip. Okay, so when you have probabilities with independent events, so A and B, so if A and B are independent events, and I ask you, hey, what's the probability event A and event B occurs? Well, that's just equal to the probability of event A times the probability of event B. And that's it. So let's try this one. So a US roulette wheel, that's a gambling wheel, all right, has 38 number slots. So it has the numbers 1 through 36, and then the numbers 0 and 00. All right, 18 of these are black, and 18 are red, and 2 are green. So the ball can land on any of these slots with equal probability. So what is the probability of red occurring on two consecutive plays? So first off, the probability um, of red occurring on any single play is, well, there's 18 red numbers out of 38. So it's 18 out of 38 or just 9 out of 19. So if we're going to play twice in a row, okay, I want to get a red number and then another red number. Well, probability of red and red. Well, whenever you see the and statement, it's going to imply multiplication. So it's the probability you get a red, which is 9 out of 19, times the probability you get another red, which is 9 out of 19, which is 81 out of 361, which is roughly 0.224. So like there's a 22.4% chance that you will get red two times in a row. All right, if two or more events are independent, okay, we can find the probability of them all occurring, again, just by multiplying. So the probability of a baby girl is 1/2. So the probability of 9 girls in a row, so if, like for example, if I'm going to have 9 kids in a row, what's the probability I get 9 girls in a row? Well, probability of 9 girls in a row, first is a girl, and second's a girl, and third is a girl, and so on. So if I want them all 9 in a row, it'd just be 1/2 times 1/2, all the way, which would just be 1/2 to the 9th power. This probability would actually just be 1 out of 512. It's a really small probability if I have 9 kids. They will all be girls. All right, let's try this one. So if the probability that South Florida will be hit by a hurricane in any single year, let's just assume that it is 519, 5 out of 19. What is the probability that South Florida will be hit by a hurricane in 3 consecutive years? So 3 years in a row, they're going to be hit with a hurricane. Well, probability of a hurricane and a hurricane, there should be an and there, and another hurricane. Well, let's just assume that they're independent here, right? Like if a hurricane happened last year, it has no bearing on if one will happen this year. So it's just the probability of a hurricane times another hurricane times another hurricane. Well, 519 times 519 times 519. That gets me 125 out of 6859, which is just a little bit more than 1% chance. So it's 0.018. So again, small probability. All right, let's try this one. If the probability of South Florida will be hit by a hurricane in any single year is 5 out of 19, what is the probability South Florida will not be hit by a hurricane in the next 10 years? Okay, so 10 years in a row without a hurricane. Well, the probability of no hurricane is 14 out of 19, which is roughly 0.737 chance. So the probability of not being hit by a hurricane in a single year is 14 out of 19. So then the probability of not being hit by a hurricane 10 years in a row, well, we're just going to take 14 out of 19, multiply it by itself 10 times. So that ends up just being 0.737 to the 10th power. So that's a little bit less than 5%, or 0.0475, or 0.047. Just a multiplying effect here, okay? All right, let's talk about dependent events now. So two events are dependent events if the occurrence of one of them has an effect, so it does have an effect on the probability of the other. Okay. So if A and B are dependent events, and I ask you, what is the probability of A and B? Well, this is equal to the probability of A times the probability of B, but given you have to assume that A just occurred, right? So to do this is a little tricky. So suppose you have won a free trip to Madrid and can take 2 people with you, all expenses paid. Bad news is this: 10 of your cousins have appeared out of nowhere and are begging you to take them. You write each cousin's name on a card, place the cards in a hat, and select one name. Then you select a second name without replacing the first. If 3 of your 10 cousins speak Spanish, find the probability of selecting 2 Spanish-speaking cousins. Well, so this is the probability the first cousin speaks Spanish and the second cousin speaks Spanish. But here's the thing, these are dependent events. Because if 3 people speak Spanish, if I take one of them out of the pool, that's going to affect the probability that another person speaks Spanish. So you're going to have to take the probability that the first person that you select speaks Spanish, and then you're going to need to multiply that by the probability the second person speaks Spanish, given that the first person you selected speaks Spanish. Well, the probability that the first cousin speaks Spanish, well, there's 10 cousins, 3 of them speak Spanish. But then when you go to get the second one, if the first person you selected did speak Spanish, well, then there were only 2 Spanish-speaking cousins left, divided by, well, if you took one person out, now there's only 9 left. So this is 3 times 2 gets me 6, 10 times 9 gets me 90. So notice how the probability that happens next changed here. So this is just reduces to 1 out of 15. There's roughly a 0.067 chance that this would happen. Let's try this one. 3 people are randomly selected, 1 person at a time, from 5 freshmen, 2 sophomores, and 4 juniors. Find the probability the first 2 people selected, all right, are freshmen, and then the third is a junior. All right. So you've got to find the probability the first 2 are freshmen, and the third is a junior. Well, how many total people are there? There's 5, 6, 7, there's 11. 5 of them are freshmen. So the probability the first person is a freshman is 5 out of 11. But if you want to select another freshman, after you remove 1 person, there's only 10 people left. But if the first person was a freshman, then there are only 4. So you take 511 times 4 out of 10 times. Now the final person needs to be a junior. Well, there are 4 juniors, but how many people are there left to select from? Well, you removed 2 people already, so now there are just 9. So this is 5 times 4 times 4 divided by 11 times 10 times 9. And that ends up simplifying to roughly 8 out of 99. So notice the subtle difference here. Usually you will do this, all right, this decreasing values like 11, 10, 9, when there's a small number of things and it asks you, oh, and 3 are selected from these 10 people or something like that. All right, let's end talking about conditional probability. So the probability of some event B happening, assuming that the event A has already occurred, is called conditional probability of B, given that A has happened. So it's denoted like this: the probability that B will happen given that A has already occurred. Okay? Calculate the probability that B happens given that A already happens. All right, let's try this so you can see an example. A letter is randomly selected from the letters of the English alphabet. Find the probability of selecting a vowel given that the outcome is a letter that precedes the letter H. Okay, so I'm giving you that the letter precedes the letter H. So we're looking for the probability you get a vowel given, so I'm telling you that the letter comes before H that you got. So this is the probability of a vowel if the sample space is restricted to the set of letters that precede H, which are the letters A, B, C, D, E, F, and G, because these precede H. So there's 1, 2, 3, 4, 5, 6, 7 letters in here. So now you need to figure out what's probably of a vowel from these letters here. Well, there are 7 possible outcomes in the sample space. So we can select a vowel from this set in one of 2 ways. You can get A or E. So the probability of selecting a vowel that precedes the letter H is just 2 out of 7. All right, let's try this one. So this is finding conditional probabilities from real world data. So this is a table that talks about mammogram screenings of 100,000 U.S. women aged 40 to 50. All right. So what it's telling is if they have a positive or negative mammogram, and if they have breast cancer or they have no breast cancer. Okay. So you can see the number of people who had positive mammograms are 720, had breast cancer 6944. So there were 7,664 here. Individuals that had negative mammograms, 80 of them actually did end up having breast cancer. This many had no breast cancer. There were this many total. You can also find the total of individuals that had breast cancer. The total of individuals had no breast cancer. And you can see that this plus this is the same as this plus this, which is 100,000. So let's assume that these numbers are representative of all U.S. women aged 40 to 50. Find the probability that a woman in this age range has a positive mammogram. So I'm telling you she has a positive mammogram, given that she does not have breast cancer. Okay, so I'm asking you positive mammogram, given that she does not have breast cancer. All right, so positive mammogram, no breast cancer. So there are this many people, okay, without breast cancer. So the probability that they have a positive mammogram with no breast cancer, well, since I'm telling you that there's no breast cancer, that's going in the denominator because you're only interested in this 99,200 people. Well, how many of those people had a positive mammogram? Well, look here, it's 6,944. So this divided by this gets you roughly 0.07. All right, so the trick here was to see that I'm telling you that there's no breast cancer, so that total here goes in the denominator, and then you just look at the people who have no breast cancer and look at the number who have a positive mammogram. All right.